I'm analyzing how well PassiveAggressiveRegressor, a machine learning model from sklearn, handles overfitting. Overfitting happens when a model learns the training data too well, performing great on that data but poorly on new, unseen data. I want to understand how to prevent this. We're using PassiveAggressiveRegressor for a regression problem, predicting a continuous value. The challenge is to figure out which statements about this model and its resistance to overfitting are correct. Sklearn is a Python library for machine learning. To tackle this, I need to know how PassiveAggressiveRegressor works, what regularization is and how the C parameter influences it, ways to stop overfitting, and what cross-validation is. This sets the stage. We are using a specific machine learning tool to predict a numerical outcome. Here's a key aspect of controlling overfitting. The C parameter adjusts the strength of regularization. Regularization adds constraints to the model, making it simpler and less prone to overfitting. A smaller C means stronger regularization, preventing the model from memorizing the training data. This statement compares PassiveAggressiveRegressor to other models like Ridge and Lasso. It claims superiority in preventing overfitting, which I need to verify. This statement suggests PassiveAggressiveRegressor inherently prevents overfitting. I'll investigate if this is true. I need to know how PassiveAggressiveRegressor works, what the C parameter in regularization does, common techniques to prevent overfitting in machine learning, like regularization and cross-validation, and how cross-validation works. This question tests your understanding of how well the PassiveAggressiveRegressor model in sklearn handles overfitting, a common problem in machine learning where a model performs well on training data but poorly on new, unseen data. I'll guide you through determining if statements about this model's behavior are true or false. Get ready, let's dive in. We're tackling a multiple-choice question assessing your grasp of PassiveAggressiveRegressor. Each choice presents a different claim about the model and its ability to resist overfitting. We'll evaluate each statement carefully. I will analyze each statement to determine whether the statement about the PassiveAggressiveRegressor's effectiveness in minimizing overfitting is true or false. Think of overfitting like a student memorizing answers without understanding the concepts. It works for the test but fails when applied in real-world scenarios. This statement is false. While the iterative updates help it adapt, it's still prone to overfitting without additional safeguards such as regularization. It's like saying a car can't crash because it has brakes. The brakes help, but careless driving can still cause accidents. This is true. The C parameter controls regularization. A smaller C means stronger regularization, making the model simpler and less prone to overfitting. Think of it as adding a constraint, preventing the model from getting too focused on minor details in the training data. This statement is false. PassiveAggressiveRegressor isn't inherently better at preventing overfitting than other regression models such as Ridge or Lasso. The best model always depends on your specific dataset and problem. It's like saying one type of wrench is always best for every bolt. This is true. Cross-validation is essential for evaluating how well a model generalizes to unseen data and for tuning hyperparameters like C to control overfitting. It's like testing a student's knowledge with several different quizzes to get a fair assessment of their understanding, not just one exam. This section emphasizes the importance of rigorous model evaluation techniques. We focus on how to measure how well our model generalizes and makes accurate predictions on new, unseen data, and how to avoid overfitting. I'm analyzing how well PassiveAggressiveRegressor handles overfitting, a common problem in machine learning where a model learns the training data too well and performs poorly on new, unseen data. I found that cross-validation is essential. It's like testing your model on different subsets of your data to see how well it generalizes. This helps prevent overfitting and tune hyperparameters such as the regularization strength, C, for optimal performance. I discovered that a smaller C parameter leads to stronger regularization. Think of C as a knob that controls how much the model is allowed to wiggle to fit the training data. A smaller C means less wiggle room, resulting in a simpler, less prone to overfitting model. I learned that PassiveAggressiveRegressor isn't inherently superior to other regression models. It's not a magic bullet for overfitting prevention. Ridge and Lasso regression also have regularization built in, and the best choice depends on the specific dataset. I discovered that passive-aggressive-regressors' iterative updates don't automatically prevent overfitting. It still needs regularization. Regularization helps prevent the model from becoming too complex and learning the noise in the training data. This section focuses on understanding how well the passive-aggressive regressor, a machine learning model, handles overfitting. Overfitting happens when a model learns the training data too well and performs poorly on new, unseen data. I'll examine whether this specific model inherently avoids this problem or needs extra help. This is a multiple-choice question testing your knowledge of passive-aggressive regressor and its ability to deal with overfitting, a common problem in machine learning. This sets up the scenario. You are using the passive-aggressive regressor model, but you're worried that it might not generalize well to new data, overfitting. You're tasked with identifying correct statements about the model's behavior regarding overfitting. This statement focuses on the "C" parameter. Smaller values of "C" mean stronger regularization. Regularization is like adding constraints to make the model simpler and less prone to overfitting. Think of it as preventing the model from being too confident in its training data, encouraging it to generalize better. This statement is true. Cross-validation is a powerful technique to evaluate how well a model generalizes. I use it to test the model on different subsets of the data, providing a more reliable estimate of its performance on unseen data. This helps prevent overfitting and fine-tune the model's settings, hyperparameters, for optimal performance. This statement is also true. This highlights the importance of understanding regularization, particularly the role of the "C" parameter, which controls how strongly the model is penalized for complexity. I'm going to need to know that a smaller "C" leads to less complex models. This points out the need for understanding cross-validation, a technique used to evaluate a model's performance and choose the best hyperparameters to prevent overfitting. This section introduces the core topic, understanding how well PassiveAggressiveRegressor, a machine learning algorithm, handles overfitting, which is when a model learns the training data too well and performs poorly on new, unseen data. We'll explore how well it generalizes to new data. This tells us we're dealing with a multiple-choice question, testing our understanding of PassiveAggressiveRegressor and overfitting. Get ready to test your knowledge. This sets the scene. We're using a specific tool, PassiveAggressiveRegressor from the sklearn library, a popular Python machine learning library for regression, predicting continuous values. I'm worried about how well it works on new data because of potential overfitting. The question will assess my understanding of overfitting mitigation within this context. This statement is incorrect. While the iterative updates are a feature of PassiveAggressiveRegressor, they don't inherently prevent overfitting. We need to add other techniques. This is correct. The parameter "C" controls regularization, which helps prevent overfitting. A smaller "C" means stronger regularization, leading to simpler, less prone to overfitting models. Think of it like a diet for your model. This is false. While PassiveAggressiveRegressor can be effective, it is not universally superior to other regression models like Ridge and Lasso for preventing overfitting. The best model depends on the specific data. This statement is absolutely true. Cross-validation is a powerful method for evaluating a model's performance on unseen data and helps tune the model's parameters, like "C", to reduce overfitting. It's a must-do for any machine learning model. This is simply a visual cue indicating the end of the question. Think of it as a visual checkmark after reading the question. This phrase sets the stage. We're tackling a machine learning problem involving the passive-aggressive regressor model, a type of regressor in scikit-learn, and the challenge of overfitting. Overfitting happens when a model learns the training data too well, performing great on that data but poorly on new, unseen data. I'll focus on this algorithm's performance and how we can improve its ability to generalize to new data. This is the core question. We are presented with multiple choice options that test our understanding of how the passive-aggressive regressor behaves concerning overfitting and how certain strategies, like using the C parameter or cross-validation, affect that. This statement is true. The C parameter controls the regularization strength. Regularization prevents overfitting by adding a penalty to the model's complexity. A smaller C means stronger regularization, simplifying the model and decreasing the risk of overfitting. Think of it like this. A smaller C encourages the model to be more conservative and less prone to memorizing the training data. This statement is also true. Cross-validation is a powerful technique to evaluate a model's performance on unseen data. It helps to avoid overfitting by testing the model's ability to generalize well on different subsets of your data. It does this by splitting your data into multiple folds, training on some folds and testing on others. This gives you a much more realistic idea of the model's performance on new, unseen data, allowing you to tune parameters like C more effectively. This is false. While the PassiveAggressiveRegressor's iterative updates can help in some situations, it doesn't inherently prevent overfitting. It needs regularization, via the C parameter, and other techniques to handle overfitting effectively. This is false. No single model is universally superior for preventing overfitting. Other regression models, like Ridge and Lasso, have built-in regularization, and which one performs best depends on the specific dataset and problem. These are the choices given in the multiple choice question. I've evaluated each choice individually above, providing explanations and determining whether each is true or false in the context of the passive-aggressive regressor and overfitting.